All right, let's do problem number 7 on page 823 in chapter 26. It says an air-filled capacitor consists of two parallel plates, each with an area of 7.6 centimeters squared, separated by a distance of 1.8 millimeters. A 20-volt potential difference is applied to these plates. Calculate A, the electric field between the plates, B, the surface charge density, C, the capacitance, and D, the charge on each plate. Okay, so let's do it. So I've got it kind of set up here with given, find, and solve. Let me zoom out a little bit. Okay, so here's what we got. It said we have a parallel plate capacitor, and it's got an area here. Now this is, when I was looking at how you guys did this problem, this is where you guys made, most people made a mistake because I was looking through a common mistake. So we're going to talk about that. And then it has a distance of 1.8 millimeters. Now, because this has 20, now I'm just going to draw a little sketch for part A. We've got this parallel plate capacitor, and I'll just draw it like this. And we've got, some positive charge on it, some negative charge, but we've got an electric field here in between the plates. And that's what we're trying to find here, right? But we have this distance D between the plates. And when you have a uniform, and you can consider, for a parallel plate capacitor, just consider the electric field between the plates to be a uniform field. And so that change in voltage is, well, let's go for the big definition is E dot ds. Okay, that's kind of the definition of a change in electric field. I think there's a negative sign in there, but we're not going to worry about that. Just magnitudes for this. And this is a constant, E. And when you add up all the ds's, you get the length across the distance across the plates. And so then I can say that the electric field, the strength of the electric field, or the magnitude of it, is equal to the change in voltage divided by the distance between the plates. This is going to be 20 volts. And the distance between the plates is 1.8 millimeters. Or we can say 1.80 times 10 to the negative, what is a milli? It's negative 3 meters. And of course, it's really important that we use meters and so on. And where did my calculator go? Here it is. So we got 20 divided by 1.8 times 10 to the negative 3. And I get 1.11 times 10 to the 4. Now, you can leave it in volts per meter, but volts per meter also reduces to newtons per coulomb. Either way is an acceptable way to express the units for electric field. Is that right? Can someone check my answers in the back of the book and so on, make sure I'm right? Okay, so that's A. I think most of you got that when I was looking at your quizzes. And then now for part B, we want the charge density. Now there's this little equation. You really should keep an equation list going as we go. And it's a sweet little equation that we derived using Gauss's law back in chapter 24. You see, these are conductors, right? We got this electric field coming down like this. And if you have a conductor with a charge on it, the electric field right off the surface of that conductor was shown to be equal to the charge density divided by epsilon naught. So it's that simple. This is going to be equal to epsilon naught times the electric field. And epsilon naught is 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. And then we have to multiply that. And by the way, let me know if I accidentally go off screen. 1.11 times 10 to the 4. Now I'm going to go from volts per meter to newtons per coulomb. because it just cancels out better. And so we have a Newton canceling the Newton. We have a Coulomb cancels the Coulomb squared, and look what I get for unit-wise. Coulombs per square meter. Woot! The units work. It must be right if the units work. All right, so sigma equals 8.85 times 10 to the negative 12 times 1.11 times 10 to the 4 equals, and I get 9.8 2 times 10 to the negative 8 coulombs per square meter. And I think the book moved the decimal over and called it like 98 nanocoulombs per square meter. I don't know. I don't care about that. I mean, you should be able to go check this and say, oh, this is the same as 98 nanocoulombs per square meter. You should be able to tell that that's right. But if you want to leave it like this, I would leave it like that. But okay, now let's do part C. Well, now, and this is the part where I saw a very easy to make mistake, very simple mistake. But you just have to be aware of it. For a parallel plate capacitor, we have C equals, well, on your equation list, you have this little thing called kappa, which we just talked about in the lecture. But and then it's the area of the parallel plate capacitor divided by the distance times epsilon naught, or something like that, right? Is that right? I think that's the right equation. And this was just, one of the reasons it told you it was filled with air is that air has a, yes?
That's 1.
Huh?
Isn't that 1?
Yeah, not 0. Thank you. Yeah, that would really reduce the capacitance greatly. It's 1. Air just is kind of like a vacuum. It behaves like a vacuum, except you can get a spark across it, you know. But anyway, so now what is the area? The area is 7.60 centimeters squared. Times epsilon, which I'll do later. Now, what is D? D is 1.80, and I'm just going to go times 10 to the negative 3 meters. I'm going to make that in meters. Well, this has to be in square meters. Now, what some of you did is you just moved the decimal place over twice, right? You called it 0.0760 square meters. That is not correct. This is square centimeters. Now, let me show you how to do this. If you say, well, 1 meter equals 100 centimeters, right? But if I just divide this by 100, I still got a centimeters there, right? It didn't cancel out. So what do I have to do? I have to square this. So it's 7.60 divided by 100 squared, not divided by 100. Does that make sense to everybody? When you do unit, take your time and just be real careful. And then we have to have epsilon naught. So we'll have 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. So let's do all the math here. I'm going to go, let's clear this, 7.6, and then I'm going to divide it by 100 squared equals 7.6 times 10 to the negative 4. I'm going to divide that now by 1.8 times 10 to the negative 3. And then I'm going to multiply that times 8.85 times 10 to the negative 12 equals, and I think this is why most of you are off by a factor of 100, because you didn't divide by that 100. So C is equal to 3.74 times 10 to the negative 12, and what are the units here? Farads. Now, times 10 to the negative 12 is fairly common. Anybody know what the abbreviation for 10 to the negative 12 is in the metric system?
Pico.
It's pico. Yeah. So you can write this as C equals 3.74 picofarads. And by the way, capacitors like that you buy at Radio Shack or some little electric store quite often have tiny capacitances like this. Actually, if you have a capacitor that is like a 1 farad capacitor, that is a huge capacitor. That sucker will kill somebody. If you bring that up to 100 volts or something and have somebody touch the ends of it, it's, yeah, curtains. It's not good. All right. And then finally, is that right, by the way? Is that in the back of the book?
That's right.
Okay. And then part D is, well, if we know the capacitance, we know capacitance is by definition the charge on the positive plate divided by the voltage difference between the plates. And so Q is equal to C times delta V, which is 3.74 times 10 to the negative 12 farads. And what is a farad? A farad, well, let's replace that farad. A farad is a coulomb per volt. That's the unit, right? For a farad, coulomb, how many coulombs of charge you get on the plate per volt that you put across those plates. And then we have 20 volts. So we just have to multiply that by 20. So I already have that. So times 20 equals, and I should have a charge of 7.47 times 10 to the negative 11 coulombs. And that's a good answer right there. But they go, this 10 to the negative 11, so close to 10 to the negative 12, right? So here's what I'm going to do. I'm going to multiply this by 10 and divide this by 10. And what I do is I get Q equals 74.7 because I multiplied this by 10. But then to keep it equal, I have to divide by 10. And when I divide this by 10, I get 10 to the negative 12 coulombs, which is 74.7 picocoulombs, which I think is what the book did, right?
Yep.
Yeah, so I'm just showing you. But this is a perfectly good answer if you just want to put them in scientific notation and just leave them in without all the pico or micro or milli or whatever. Okay? Let me zoom all the way out. So take a look. Take a look. What do you think? Any questions on that? Okay. That is